Hi everyone, welcome back. This video is about understanding Faiss, F-A-I-S-S. We'll talk about what it is in a minute. And in fact, to better appreciate this approach, I recommend watching the last video if you haven't done that, where we took VGG16 pre-trained on ImageNet architecture and combined that with cosine similarity for, to basically build a image search engine. Yeah, an image retrieval engine. And you'll appreciate this better. Of course, we'll talk about cosine similarity in this context also, which is nothing but the cosine of two vectors, one being the one that you're comparing to, and the other one is a vector from your index. Okay, none of that makes sense. Again, hopefully as we go along, it should hopefully make more sense. And before jumping to the next slide, again, as usual, if you want to be notified of these, it helps if you subscribe to this channel. So hit the subscribe button down below. And right now, pause, do that. And while you're there, do not forget to click the thanks button if you're feeling extra generous. Okay, so let us try to start to understand what Faiss is all about. And in fact, I'm going to do my best in making sure you understand what it is, but nothing beats going through the original paper. So here is the first one. When they proposed it for the first time back in 2017, it's already 7 years now, right? So the days are going by pretty fast. Anyway, so here the title is Billion Scale Similarity Search with GPUs. So obviously it should tell you two things. It's leveraging GPUs, not just CPU. And also it's designed to work with like billions scale. So that's what it basically means. So it must be more efficient than what we are doing, using traditional tools. Now, recently, in fact, a couple of months ago in 2024, September, the same team actually released another paper titled the Faiss library, where they kind of provided a bit more insights into this library that we're going to use in Python. So I definitely recommend you to deeply actually go through these two papers. But at a high level, you can see Faiss is a toolkit of indexing methods. So it's primarily an indexing solution, right? Efficient indexing and relative primitives used to search blah, 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 whatever it is, right? So, but ideally, I mean, the key lesson from here, if you need to learn one thing, is it's a toolkit for indexing methods. On top of that, once it's indexed, you are using the search tools to actually match your query with the efficiently indexed database, and then you're retrieving the information from there. Okay, so that is what Faiss is all about. Okay, done with the video, right? We are going to look at code, as you probably know. Okay, so here is my definition. Not my definition is different from others. I just took what they mentioned there. So Faiss, it's a library for efficient similarity search and clustering of dense vectors. What does that mean? You have a whole bunch of vectors, lots of vectors, and you want to perform some sort of a similarity search because you have a vector and you want to compare it, then Faiss is an efficient library. And of course, if you also want to do clustering, this is also a good library for that application. And why? Because it's optimized for searching through millions or billions of high dimensional vectors very quickly. Even on a CPU, you will see very big advantages. That's what I'm going to show you today. But if you take it to GPU, everything is going to scale very nicely on GPUs. It contains, by the way, did I ever define what Faiss stands for? It's actually Facebook AI Similarity Search, I believe. That's what, did I do it anywhere? I should have done that. That's such a basic stuff. Or maybe did I do it on the front? Okay, sorry about that. It's Facebook AI Similarity. I believe the last S stands for search. So there are two main approaches that I'm going to talk about. They have multiple approaches defined as part of Faiss, but primarily two main approaches because these two are different, right? So one is index flat L2. L2 is the same L2 as you find in L2 regularization, for example. You may be exposed to that term before. But basically what it's doing is it's an exact L2 matching but faster than manual implementation. So what does that mean? So index flat L2 is very similar to the process that we covered in the last tutorial, where we extracted a whole bunch of features, and then you're doing a brute force cosine similarity between a couple of vectors. Here it's doing very similar approach, L2 matching, except they claim that, or it is supposed to be faster than manual implementation, which is what we have done in the last tutorial. Well, why faster? Because they have done some optimizations in terms of the indexing. So even though this is kind of brute force, slightly more efficient version. Now, IndexIVF, IV F stands for inverted file, by the way. IndexIVF is the one where I see a lot of enhancement, not enhancement, what is the term? Efficiency, let's say. That's the most efficient one for search-based applications, because while indexing, it clusters similar features together. So when you're performing a search, it's not searching for all the vectors. It's first identifies, okay, so based on your query vector, here are a couple of regions that are relevant for this search, and I'm not going to even look at all the other regions, only in these two regions. That improves this throughput tremendously, right? So I already mentioned, so it's similar to our cosine distance matching, but which means you may not notice any speed difference. I'm talking about flat L2, the first one here. Especially for smaller data sets, you may actually find no difference, or in fact, you may find the cosine being a bit more efficient than this approach. But that's why flat L2 is okay. But for large data sets, you absolutely need IVF, IndexIVF. If you really care about speedy results. Okay, now again, why is this faster? Because it reduces the number of comparisons needed through clustering, because it actually pre-clusters. So it only looks at the relevant clusters and not through every data point, which really helps when you have billions of images that you're trying to search. Okay, so here is something we are going to do today as part of the code to gain better understanding of what's going on. But here, a synthetically generated vectors plotted on this three-dimensional plot right there, and the query vector. For example, let's say, hey, this is the vector that is my query vector, unknown image, for example, and I want to find the similarities. Where are the similar images in this space? And if you use cosine similarity, this is brute force cosine similarity. I call it brute force because you're kind of matching this vector against all the other 1,000 vectors that you have in this space. If you have 1 billion, it's going to match against all the 1 billion and going to rank them and tell you, hey, here are the top 3 matches, which is very close. So what's the point of searching this entire space if you know that the solution space is right around this initial vector, right? So that's what the IVF actually solves. But if you do exactly the same search, by the way, I changed the screen and you probably didn't even notice, because look at the top right there. Sorry, look at the top right here. It says L2 search results. If I go back, it says cosine similarity results. The screen looks exactly the same. I'm not printing the same and putting a different title on it. This is actually a different result, which is identical. That's why, because the approach is identical. This is Faiss L2 search results, which is Faiss indexing plus L2 to actually find the L2 distance between the top 3 matches, and that's what we're printing here. Now, the last one, which is obviously the one I've been rooting for, is the IVF search results. And as you can see, different clusters. So it pre-clustered this, and I selected this to be 10 regions. Why is it showing only now? Oh, yeah, region 0. So it's showing you all the 10 regions that I kind of defined. I selected the space to be divided into 10 regions, and that's what the different colors mean. And now when it performs this search, it's not even going to look at this purple or probably all the blue and everything. It only looks at a cluster or a couple of clusters that are relevant to the data point, and then finds the solution. So this is going to be orders of magnitude, I think at least 3 to 4 orders of magnitude faster results even on a laptop. So we'll establish that later on. So that's what we have here. And finally, yeah, so this is a test I have done. We'll look at the results again in a minute. But for 1,000 queries, like here is the number of vectors. We have 1,000 vectors that we are comparing against our query vector. And here is 10,000, 100,000, and a million, right? So as you can see, these two approaches, the top orange one is the Faiss flat L2. And as I mentioned, this and the brute force cosine will be very similar in terms of execution time, and they are both are scaling very linearly, as you can see, as a log function of the number of vectors. And if you look at the green one, which is the IVF, it is of course still scaling up. I should have done like 10 million and so on, but again, it takes a lot of computing time on a CPU. I encourage you to do that exercise to see how this actually gets scaled compared to the other two as the size increases. Even with 1 million, you can see 1 million vectors, the search time is 1, 2, 3 orders of magnitude, much faster compared to the other two approaches right here. So this is the take-home message, I would say. But if you're wondering, okay, you mentioned about all of these, like, do I use IVF all the time and all that? If you can, sure, nothing wrong with that. The advantage of cosine or flat L2 is it's easy to implement, right? Like cosine, even this one is easy to implement. These work very well if the data set is small. And in fact, these are very accurate because you're comparing against each and every one of these. You're not pre-selecting some clusters and saying, I only want to look at this. So there is something you're potentially giving up with the IVF approach, right? So if you can tolerate approximate results, but I don't want to stress a lot on this because the search results are going to be very good. At least based on my testing, the search results are in fact excellent. I'm getting exactly the same results in both cases when I tested these with images. Again, stay tuned for the next video where we implement this for image search application. Okay, so but for all practical purposes, if you ask me, I'll just pick IVF all the time. But cosine is so easy. You can easily implement this, and if you're going to work with 1,000 images or 1,000 pieces of data, I keep calling them images, whatever, anything you can convert to vector, your search space has 1,000 vectors or fewer, or even a handful of 1,000. The cosine or flat L2 are fine, but IVF uses flat L2, by the way. We'll look at the code in a minute, but otherwise this can be a better approach, provided you're willing to spend some time in indexing, right? This takes a bit because it needs to perform the clustering and save all the information and all that. Okay, which I guess we do only once. Okay, with that information, let's go ahead and jump into our code. And the code here is all about synthetic data. Here, we're not working with real images. We'll save that for next tutorial. So please, again, subscribe. Stay tuned for the next one. So here, what are we doing? So I'm importing the NumPy, Matplotlib, scikit-learn. The only reason why I'm doing scikit-learn is to kind of normalize the data. Faiss is the library. I installed Faiss -CPU. That's what, because this is a CPU system. There is a GPU version. So go ahead and install that if you have access to GPU. And that's it. So everything else is like plotting and time. So let's go ahead and run this. I'm going to run these line by line so we can see some results, although these are just functions that I'll just walk you through. Now, this is as simple as it gets. So I'm saying, okay, generate 100 vectors of dimension 3. That's all we're doing. Random vectors. So random number of vectors, number of dimensions. Basically, it's part of NumPy function anyway. So we do that. And here we are plotting those vectors. That's it. Yeah, so nothing new. So let's go ahead and run these two lines. And let's run them. Select up to here. Okay, so though that is done. So now come down and plot vectors with regions. I had to write this one separate because I already did this one, and I'm like, oh, I don't want to modify that. And I added this because I want to show different regions for the IVF plot. So this is basically it. You can potentially combine both into one. I don't know why. Kind of got lazy, or I should have asked ChatGPT to combine them together. Either way, doesn't matter. Okay, that's just plotting. Okay, now compute vector assignment. So basically it's looking at, okay, which vectors belong to which centroids. So that's what we're doing. And here we are looking at index flat L2. and basically it plots, gives you the centroids right there. And while we are here, let's go ahead and talk about the k-means. Again, k-means obviously divides your data into how many of our clusters you define, and that's what is happening here. And I'm using the k-means from Faiss library, so just to make sure everything is together, but it doesn't matter. I guess it doesn't matter. I haven't tried scikit-learn or any other clustering k-means available at multiple places. So why not use the one from Faiss? Okay, so you got the k-means there, and brute force cosine search is very similar to what we have done in the last tutorial. So we are just doing the dot product right here, and we are just sorting them based on the similarity. So this is basically it, right? I mean, the dot product between two vectors is proportional to your cos theta. In fact, you divide that by the magnitudes, then you get the actual cos theta values. So this is your brute force way. So we're going to do this three different ways, right? I mean, we're going to compare our query vector against the vectors, all the 1,000 vectors that we just generated, three different ways. One is the cosine search, which is what we just did. The other one is flat L2 search, which is nothing but index flat L2 from Faiss library. And then I'm timing them so we can actually compare how long each of these approaches take. And finally, the search results. I should have renamed this realistic to IVF search, because I started off with just very simple IVF search, just like here, and I had to modify this to kind of incorporate a couple of things like, okay, separate the training from the search time, because I want to time each thing separately, and I deleted the other function but forgot to change the name, but still it doesn't matter. It's the same. I mean, it should work. It's not like I'm not calling this function. Okay, so done with functions. Now let's go ahead and go through these in a very methodical way. So step number one, we need to generate or sample data for visualization. So how many vectors? 1,000, a three-dimensional vector, so we can plot it in a three-dimensional space. In reality, you may have, like in VGG16, you have 512 vectors, right? Feature vectors. If you're using vision transformers, you may end up with 768 feature vectors. So whatever those vectors size is, that's how many vectors you're dealing with in reality. But for visualization purposes, I picked a dimension of 3. You can generate a 512 size vector and then collapse it into using principal component analysis, but what's the point? Like I did in the last tutorial, by the way. So we just generated a database of vectors right there, and we have our database of vectors. Thought of looking at the variables, but yeah, we have 1,000 vectors with 3 dimensions. Okay, now let's go ahead and randomly generate a query vector, because we need to match this query vector with this other vector. So which means we are only generating one vector. That's it, using the same function. Now let's go ahead and visualize. So we have the plotting for 3D without the regions. So let's go ahead and visualize that. And there you go. So this is what I showed you earlier. So this is the space, and this is where our query vector is. Okay. Now that we have this, let's go ahead and perform a match. Here is the query vector. Here is the potential solution space. So what are the 3 best matches? So let's go ahead and print those out. And this is brute force, right? So basically top find cosine similarity matches. In fact, not top 3, top 5. So this is the time it took was 0.30999 seconds. And these are all the top 3. So the indices are 0, 653, 61, 273, 336 in this space. Why am I printing that out? Because I want to see how the L2 search actually performs, and is it giving the same result or not. But before that, you can actually plot, okay, the solution. Where are those 3? And it should show us those 3, like right. Obviously, it makes sense that they are very close to the other one. Let's do exactly the same exercise for L2 search. Remember, we already defined the L2 function earlier. All I'm doing here is just calling that function. And you see how it says 0, 653, 61, 273, and 336. It should be exactly the same. 0, 653, blah, blah, blah. Oh, God, I should. Later on, we'll print everything at once. Why is it doing that? Am I missing something? Oh, right there. 0, 653, 61, 273, 336, 653, 61, 273, exactly identical, exactly the same thing. Okay, so now let's perform the IVF search, the realistic search that I call, and let's see how, how the result looks like. So now let's, by the way, so first, the way you perform that is for this IndexIVF flat, you need to provide a quantizer, and the quantizer we are providing is index flat L2. So it is performing that, except it's using that as a quantizer, and then it creates this number of regions. And when the time comes to search, we are only searching in those specific regions, so it saves us, or the relevant regions, so it saves us all that time, right? In not searching elsewhere. Okay, where was I? Okay, let's go ahead and run these and print, whatever, print all the way up to here. And you can see, okay, so training index time is always slower, right? I mean, you're going through all these images and you're doing this, and search time is literally nothing. Oh, not search, the adding time right there. Let's go ahead and do actual search, set number of regions to search, because you can actually say, hey, search the only region, one region where the solution is, or you can search like, okay, the 3 nearest regions for the solution space. So search the number of regions. Basically, let's go ahead and perform that, get the centroids, and go ahead and print the whole thing. Okay, so here it is. So it's searched 3 out of 10 regions. It searched regions number 4 to 3. It doesn't make any sense unless you see what those 4 to 3 are on the screen. But anyway, it's printing out what we asked it to do. And now comes, okay, let's go ahead and visualize what it actually is showing us. And this is basically, I shouldn't have shown you the screens, but some people don't have time to go through the entire video. So for those, the initial presentation probably answered the questions. So there you go. So it's giving you these 3, and they're the 10 regions, and it's actually searching probably these nearest regions, in coming up with this solution. Now let's go ahead and compare all the results at one place. There's a reason why I've written these, so you can actually see all the results. So here you can see, am I printing the right thing? Yeah, I am printing the right thing. So the results between, so cosine versus basic, like all 5, you see these are all the exact regions, like it found, not regions, the dots, the solution vectors, 0, 653, 336, 273, 61, same thing here, 653, you get pretty much the same answer. So that's why I think you're not compromising anything by going with IVF. In fact, you're speeding things up so fast, there's no reason not to use it. So finally, okay, that was for 1,000 vectors, but how do things scale? So this part is basically doing exactly what you saw earlier, except we're going through a list of 100,000, 10,000, and 100,000, and let's do the plotting and end the video on that note. So I hope really you are learning something here. You're learning about Faiss, you're learning about what IVF is, how it is different from the flat approaches. There are a couple of flat approaches. The flat L2 is something I showed you earlier. Flat is basically, almost think of it as brute force in a way. The others, like IVF, for example, are dividing the space, are using some tricks to kind of divide the space into different clusters, and you're kind of only searching a smaller area, a region. So that's the most efficient way of doing things. So as you can see on the screen here, it obviously it finished with 100 vectors pretty quickly. You can obviously see the advantage of IVF even on smaller data sets, like 100 vectors. It's like very, very little time. And then the real benefit shines when you are testing with more and more of these vectors. This 100,000 may take, again, this is CPU. GPU would be much faster. But the relative difference, I don't know, probably on GPU is much better if you're looking at IVF. But let me pause the video and let's just look at the final curve, which you already did, the graph, just to see how IVF is better than the other 2 approaches. Okay, it seems to be done right now, and you can look at the values here, but obviously can I move this? Okay, there you go. So hopefully you can see the result right there. So the green is our IVF, scales very nicely, and you see 3 to 4 orders of magnitude in terms of how much faster the IVF is. And I'm a bit surprised to see the brute force cosine actually doing much better compared to the Faiss flat L2. But maybe the flat L2 performs better on a GPU system compared to cosine, because that is one of the key aspects of Faiss library, right? I mean, leveraging GPU and better hardware. So that's something, if you guys can do that and at least post a result, that would be great. Okay, thank you very much. And in the next tutorial, we are going to apply our IVF, which we established is the best for image retrieval application. So I'll see you there. Thank you.